So in our last video, we looked at what it means for a point to be the circumcenter of a triangle. And in this video, we're going to learn about another special point for a triangle called the incenter. So let's take a look. So you can see here again on GeoGebra, I have a triangle ABC. Right now, it's an acute triangle. I can stretch the corners around. I could make it more of an obtuse triangle. I could make it look pretty much like a right triangle. Can make it look pretty much like an equilateral triangle if I wanted to. Doesn't really matter, so I'm just going to kind of make it just some kind of acute triangle for now. And then what I'm going to do is I'm going to put the angle bisector in for, we'll start with one angle in this triangle. So I'm going to grab my tool that lets me do an angle bisector, and I'm going to bisect first angle B. So you can see I've bisected angle B, which means I've split it into two smaller angles. And now I'm going to bisect another angle. I'll bisect angle C next. So we'll put the bisector for angle C in there. And like we would expect, there is a point of intersection. Point D right there is the point of intersection. I don't know if I got that exactly where I wanted it. Oops, lost my angle bisector. Let me put that back on there. And then let's do the point of intersection for those two objects, point D. So since they're two lines and they're in the same plane and they're not parallel, we do expect them to intersect, and that's what happens at point D. They intersect at point D. If I were to move around the corners of the triangle, then you can see that intersection, it's still going to exist because no matter how I move the corners around, I'm still going to be bisecting those two angles. One difference that you'll notice is no matter what I make this triangle look like, whether I make it an obtuse triangle with an obtuse angle there at angle C, or I make it more acute, or I try to make it more or less a right triangle or an equilateral triangle, that point D, it's always ending up inside my triangle. So that's one difference between the incenter, which is what we're going to find out that is, and the circumcenter. It's always inside the triangle. But I got that point of intersection between two of the angle bisectors. But now we're going to take a look, and you guys might be able to predict that this is going to happen. I'm also going to bisect the third angle in my triangle, and I'm going to notice that it too goes through the point D. So what we have is a situation, much like in the last video with the circumcenter, where I've bisected all three angles this time, and all three of those angle bisectors are intersecting right here at this point D. And that takes us to Theorem 5-6. Theorem 5-6 says the angle bisectors of a triangle, and we'll go ahead and finish that, the angle bisectors of a triangle all intersect. There will be three of those angle bisectors, since there's three angles, all intersect at a single point. At a single point. That point is called the incenter. And that point has a special quality to it. Much like the circumcenter had a special quality, the incenter also has a special quality. And to kind of see what it is and to make sense of what that special point, the special quality that special point has, we'll think about, well, let's get rid of a couple of these angle bisectors. So I'm going to get rid of, temporarily, I'm going to make two of these angle bisectors disappear. So we'll pick two of those and make them go away. Now point D is on the angle bisector for angle B. And we learned that any point that's on the angle bisector for an angle is going to be equidistant from the two sides of that angle. So let me just show you that on my program here. I'm going to measure the distance between point D and side C, and I'm going to measure the distance between point D and side A, and you're going to notice that those two distances ended up being the same, which is what we would expect, right? We would expect that since point D is on the bisector of angle B, that point D would be equidistant from both sides of that angle. But we also need to remember that point D is also on the angle bisector for angle A. So let's put the angle bisector for angle A back on the screen. Now remember, this measurement of 1.75, this guy right here, that's the distance from D to this side. This is the distance from D to this side. But now D is also on the angle bisector for angle A here. So we would expect that it's the same distance away from segment AC as it is from segment AB. So this distance from D to C to segment C should be the same as the distance from D over here to segment B. Let's just kind of verify real quick that it is. Let me grab my measuring tool. I'm going to measure the distance from point D over here to segment B, and I can see that it is also 1.75. And if I were to put on the bisector, let's see, which one haven't I put on? I haven't put on the bisector for C yet, but the bisector for angle C, D is on that bisector. So as we would expect, it is D is the same distance away from segment A, 1.75, as it is from B, 1.75. And so what that means is that point D, which again was the incenter because it's the point of intersection for all the sides, it's the point of intersection for all the angle bisectors of my triangle, it's the incenter, it means that it is equidistant from all three sides of my triangle. So that's going to be kind of the second part of this theorem that we can put on here. That incenter, the incenter, is always equidistant from the sides of the triangle. So our theorem 5-6 tells us that if we do all three angle bisectors of a triangle, they're all going to intersect at a single point called the incenter. So that's point D in my picture. And that incenter is the same distance away from all three sides. It's equidistant from the three sides of the triangle. Now, if you remember, we learned that the circumcenter of a triangle is also the center of a circle, a special circle that contains all 3 points of the corners of the triangle, all three vertices of the triangle. And that was another special quality of the circumcenter. Well, the incenter is also the center of a special circle. Only this time, it's not the center of a circle that connects all three corners of the triangle. Let me show you what it's the center of. So what I'm going to do here first is I am going to, on my picture, I'm going to get rid of the three angle bisectors. I'm going to take those off of there. So take those off. I'm going to take off these points E, F, and G, which were the intersections of the angle bisectors and the sides. And I'm going to get rid of these measurements that are on the screen as well. So I'm just cleaning my picture up a little bit. So what I have now is I have D, which is the incenter, and I have my triangle. Now I am going to put in a segment that's representing the distance from D to, let's say, segment AC. So let me show you what I'm going to do. I'm going to go in and I'm going to create a segment that is perpendicular. Oh, well, all my stuff showed back up. Let me just take that all away again. I don't want all that on there. I want this to look a little bit cleaner. So give me a second. Make all of these things hidden. Okay, and so I am going to create a perpendicular line going from point D to segment AC. All right, so there's this perpendicular line. I'm going to create the intersection between those two objects, and then I'm going to get rid of that line, and now I'm going to put a segment going from D to H. Okay, now that segment is perpendicular to segment AC. Let me just put a right angle on there just to show that it is perpendicular. So we got a right angle there, right? It shows that segment DH is perpendicular to segment AC. And that segment DH represents the distance from D over to this segment. Now I could have done the same thing from D down to this segment and from D over to this segment. And since that incenter is equidistant from the different sides, all of those segments would be the same, right? A segment that goes from here down to here would be the same length as a segment that goes from here over to here. As long as I'm going perpendicularly over to the sides of the triangle, all three of those segments would be the same length. What I'm going to do is I'm going to create a circle that has its center at D and that contains point H there. And you might be able to predict what's going to happen next. So I'm going to center my circle at D, make it go through H, and what do you notice? Well, of course, it goes through H, which means it just touches segment AC at H only. It also just barely touches segment AB, and it also just barely touches segment BC. In fact, if I just kind of highlight those intersection points, I can do that real quick. Intersection between that and this segment, intersection between that and this segment. You can see I have these 3 points, which is where this circle, which has a center at the incenter of the triangle, that circle only touches each side of this triangle at one place. And so that circle is called an inscribed circle. So let me put some notes over here. The incenter is the center of an inscribed circle for the triangle. And an inscribed circle means a circle that only touches each side in one location. It intersects each side of our shape at exactly one place. So I'll kind of write that over here. I think I can write right on top of here. An inscribed circle means a circle that intersects each side of the triangle at exactly, oh, I didn't spell exactly right there, exactly one point. So that incenter, point D, is the, I don't know what happened to the stuff I had written over here. Sorry, hopefully you can go back and rewind if you need to write that down. But that incenter is the center of what we call an inscribed circle for that triangle. And the inscribed circle is the circle that's going to have a point of intersection at one point for each side of the triangle. Its radius, the radius of my inscribed circle, is going to be the distance from the incenter to each side of the triangle.